Ever wondered how Google translates an entire web page to a different language in a matter of seconds? Or your phone gallery groups images based on their location? All of this is a product of deep learning. But what exactly is deep learning? Deep learning is a subset of machine learning, which in turn is a subset of artificial intelligence. Artificial intelligence is a technique that enables a machine to mimic human behavior. Machine learning is a technique to achieve AI through algorithms trained with data. And finally, deep learning is a type of machine learning inspired by the structure of the human brain. In terms of deep learning, this structure is called an artificial neural network. Let's understand deep learning better and how it's different from machine learning. Say we create a machine that could differentiate between tomatoes and cherries. If done using machine learning, we'd have to tell the machine the features based on which the two can be differentiated. These features could be the size and the type of stem on them. With deep learning, on the other hand, the features are picked out by the neural network without human intervention. Of course, that kind of independence comes at the cost of having a much higher volume of data to train our machine. Now, let's dive into the working of neural networks. Here, we have 3 students. Each of them write down the digit 9 on a piece of paper. Notably, they don't all write it identically. The human brain can easily recognize the digits. But what if a computer had to recognize them? That's where deep learning comes in. Here's a neural network trained to identify handwritten digits. Each number is present as an image of 28 × 28 pixels. Now, that amounts to a total of 784 pixels. Neurons, the core entity of a neural network, is where the information processing takes place. Each of the 784 pixels is fed to a neuron in the first layer of our neural network. This forms the input layer. On the other end, we have the output layer, with each neuron representing a digit with the hidden layers existing between them. The information is transferred from one layer to another over connecting channels. Each of these has a value attached to it, and hence is called a weighted channel. All neurons have a unique number associated with it called bias. This bias is added to the weighted sum of inputs reaching the neuron, which is then applied to a function known as the activation function. The result of the activation function determines if the neuron gets activated. Every activated neuron passes on information to the following layers. This continues up till the second last layer. The one neuron activated in the output layer corresponds to the input digit. The weights and bias are continuously adjusted to produce a well-trained network. So, where is deep learning applied? In customer support. When most people converse with customer support agents, the conversation seems so real, they don't even realize that it's actually a bot on the other side. In medical care, neural networks detect cancer cells and analyze MRI images to give detailed results. Self-driving cars. What seemed like science fiction is now a reality. Apple, Tesla, and Nissan are only a few of the companies working on self-driving cars. So, deep learning has a vast scope, but it too faces some limitations. The first, as we discussed earlier, is data. While deep learning is the most efficient way to deal with unstructured data, a neural network requires a massive volume of data to train. Let's assume we always have access to the necessary amount of data. Processing this is not within the capability of every machine. And that brings us to our second limitation: computational power. Training a neural network requires graphical processing units, which have thousands of cores as compared to CPUs. And GPUs are, of course, more expensive. And finally, we come down to training time. Deep neural networks take hours or even months to train. The time increases with the amount of data and number of layers in the network. So, here's a short quiz for you. Arrange the following statements in order to describe the working of a neural network. A. The bias is added. B. The weighted sum of the inputs is calculated. C. Specific neuron is activated. D. The result is fed to an activation function. Leave your answers in the comments section below. 3 of you stand a chance to win Amazon vouchers, so hurry! Some of the popular deep learning frameworks include TensorFlow, PyTorch, Keras, Deeplearning 4j, Caffe, and Microsoft Cognitive Toolkit. Considering the future predictions for deep learning and AI, we seem to have only scratched the surface. In fact, Horus Technology is working on a device for the blind that uses deep learning with computer vision to describe the world to the users. Replicating the human mind at the entirety may be not just an episode of science fiction for too long. The future is indeed full of surprises. And that is deep learning for you in short.
This is a decision tree. Right now, it's learning. When it's done, it'll have learned to do something very human. Something that everyone knows how to do, but no one can quite explain how they do it. Something that has fooled generations of brilliant scientists with its apparent simplicity, but practical complexity. Something that has only become possible in the last few decades, thanks to creative solutions in the face of huge complexity. It's learning to see. Let's test it out. With the help of a camera and a computer, our decision tree sees exactly how many fingers we're holding up. Now, depending on who you are, the fact that a machine can perform this task may be completely mind-blowing, not all that out of the ordinary, or may not even be all that impressive. The good news here is whichever camp you're in good company. Our finger counting machine is a simple example that belongs to a deceptively complex class of problems. Problems that arise from thinking about how we think. How exactly is it that you, me, and other animals can so easily turn images into ideas? How with a single glance do we so accurately identify objects? Historically, questions like these have led very smart people to very wrong conclusions. AI researchers of the 1960s were seduced into believing that the AI problem was much simpler than it actually is. The first attempts at our problem, programming a computer to make sense of images, were no exception. When the brilliant AI researcher Marvin Minsky set out to solve our problem in 1966, he assigned it to an MIT freshman, Gerald Sussman. Minsky and Sussman began programming their mainframe computer to describe images they fed it from a video camera, and ambitiously set out to complete the task in a single summer. As Minsky and Sussman quickly learned, programming computers to see is hard. Like, really hard. To see why, let's look at our problem a little more closely. We'll start with a photo shoot. If we're going to program our computer to count fingers, we need some data to practice on. Using a leap motion infrared sensor and some Python code, we'll take some pictures of hands. We can have a look at our data using a tool our early AI counterparts could only have dreamed of, the Jupyter Notebook. We'll import our images and have a look at the first one. Cameras, like the one in our leap motion sensor, and our eyes to some extent capture light in discrete blocks called pixels. Our images are made up of 100 by 100 grids of pixels, where each pixel is completely described by an intensity value between 0 and 255. We can now begin to think about how to count the number of fingers in our images. To count fingers, we first need to find them. More specifically, we would like to know which pixels in our image belong to fingers. Let's consider a few example pixels. For each pixel, we certainly don't need to consider the entire image to decide if the pixel belongs to a finger or not, so we'll focus our problem by sampling a 9 by 9 grid around each example pixel. We now have a much more clearly defined problem. Given a 9 by 9 example, we need to decide if these pixels show a finger or something else. This is easy for us to do visually, but we have to remember that our computer is completely unaware of what an image is. We see fingers thanks to our visual cortex, but our computer just sees numbers. Our algorithm must decide if it sees a finger or not based completely on these 81 numbers. Is there some mathematical equation or set of logical rules we can plug our 81 numbers into that will output the correct labels? If so, how do we find it? How do we even start? What patterns in our 81 numbers should we look for? How do we decide which patterns represent fingers? How do we account for the different hand orientations, shapes, sizes, and distances to our camera? In this series, we'll answer these questions and ultimately build a robust solution, a decision tree. A lot has changed in the 50 years since Minsky and Sussman set out to solve problems like this. One particularly interesting shift is the discovery that many of the things that make our problem hard also make lots and lots of other interesting problems hard too. These intersections mean that the approach we'll use to build our decision tree applies far beyond finding fingers in images. Today, decision trees can play chess, detect car crashes, diagnose disease, predict heart attacks, detect credit card fraud, reveal hidden structure and data, and do lots and lots of other useful things, all with a single algorithm. Next time,